Thank you everybody for joining us today. So we're going to be talking about some no and low cost plant upgrades, just some simple process changes and things you can do at your facilities that can have beneficial impact on process quality and energy consumption at your facilities. Um, Real quick, I'm just doing an introduction and some housekeeping about the CDAC program here. Who we are. CDAC is an applied research program at the University of Illinois based in Urbana-Champaign. Um, we assist communities and buildings in achieving energy efficiency, saving money, becoming more sustainable. The Public Water Infrastructure Program is one of the programs that helps us achieve that. And our overall goal is to help reduce the energy footprint of Illinois and beyond. So a little bit about the Public Water Infrastructure Program. It's sponsored by the Illinois EPA Office of Energy to help provide no-cost energy assistance and technical assistance to publicly owned wastewater and water treatment facilities in the state of Illinois. So we help provide a comprehensive report. We're going to list in that report potential energy savings measures for your facility. We rank those from shortest to longest payback period. And we kind of categorize those into groups so you can see some quick impacts from short-term projects. Then you've got some longer-term planned projects that you can look forward to. We do some estimated economics, give you an idea of what the payback period is going to be, what your capital expenditures might be. And we also link you to funding sources such as utility incentives, grant programs, and low interest loans. And then we also provide continuing education for operators such as today's webinar. If you're interested in an assessment or more information, you can visit us at www.smartenergy.illinois.edu/water. Why might you want to complete an energy assessment? If you've got an older system or you haven't had a previous assessment, we can help you identify some missed opportunities, plan for capital improvements in the future, uncover potential possibilities for your plant, or we can provide third-party support for the treatment plant personnel's ideas. A lot of the operators have ideas that they just need a little bit of support to push the budgetary committee to fund those things. We can help provide that assistance. What if you have a brand new plant or you've recently upgraded it? We always find that there's more ways to improve. There's always something that got cut out of the budget or left on the table, and we can help identify what those were and what kind of impact they could have for your facility. And there's also always new technologies and processes in development. This is a constantly innovating industry, so we can help you identify maybe there's something that you haven't looked at before that might be beneficial for you. As far as applying for an energy assessment, you can go to our website and find an application there. You have to be located in Illinois and be publicly owned. Got to be willing to allow us to come out to the site, view the facility, take pictures, gather documentation, things like that. And then we do share that final report with the energy office. It's non-regulatory, so we're not going to be out there finding things that are going to violate your permit or anything like that. There's no hassle involved. We're just coming out to see where you can save energy, where you can improve the process. And then we share that with the energy office to help keep track of the program's effectiveness. The second step is data collection. We'll jump on a call with you, go over some detailed information about your facility. We'll gather utility information and your DMRs. We try to make that as easy and painless as possible for you. So if we can pull any of that information ourselves, we'll do that. For most of the utilities, we can pull those bills. We just need the account number, and we can pull DMRs ourselves from the EPA's online database. And then we schedule the site visit, come out. Generally takes us a couple hours on site. We'll be taking pictures of the process, documenting what's going on. But joining me today, we have Dr. Larry Moore. He's going to talk a little bit about some activated sludge strategies to help improve process control and reduce energy consumption. And then Nick Newman's going to talk about what Kishwaukee Water Reclamation District has done with some of their materials. But to kick things off, since they're both talking about activated sludge, I'm going to touch a little bit on lagoon strategies and what you can do with aerated lagoons to help improve the process and reduce energy consumption. One of the big things is a lot of lagoons can take some advantage of algal DO production. During the daytime, they're producing DO, and that can hit sometimes 200 to 300% of what your DO requirement needs to be for treatment. But then at night, that algae starts to die off. It starts to actually consume that dissolved oxygen, so you have to increase aeration during the nighttime. So there are ways to kind of schedule your aeration through either time switch controls or with VFDs to take advantage of that fluctuating DO output from algae. Um, Something else that contributes a bit to algal DO is, the larger surface area you have, the more air contact the surface of that water has. If you're mixing that water, um, you're driving some surface contact DO into the lagoon. Um, Generally not as large amount as you get from algae or from actual mixing technologies, but there's some impact there as well. On a windier day, you get some wave action. You might get a little bit more DO. So if you have an ability to track DO in your process, you can make some adjustments for those um, through controls. Looking at surface aeration, many different types, looking at somewhere around 1.5 to 2.1 kilograms of oxygen per kilowatt hour, putting DO into the lagoon. The nice thing about surface aerators is that they can be more easily moved around than if you have a subsurface aeration system. And we'll touch a little bit on how you can take advantage of that for improving lagoon processes. But by the numbers, we would expect somewhere around 7 to 20 horsepower every 24 hours for a plant with about 300 pound of BOD per day loading. When we get to subsurface aeration, looking at those aerators, you get a little bit more oxygen transfer efficiency because you're delivering oxygen at depth and letting that rise up with bubbles. So there's also greater surface area contact. So about 3.7 to 4 kilograms of oxygen per kilowatt hour with fine bubble and coarse bubble aeration. So looking at a lagoon, we expect that to be somewhere between 5 and 8 horsepower for about 300 pounds of BOD per day. Downside to having subsurface aeration is a lot of times you're a little bit more limited in how you can place those in a lagoon. Sometimes it's rigid piping, sometimes it's flexible, but you have shorter runs. You don't have the flexibility and placement of aeration that you have with surface mixing equipment. So depending on how your lagoon is set up and staged, there is a risk of developing a short circuiting situation, and aeration placement can help break up those short circuit paths. Also, over time, you get sludge mounding where you don't have aerators located, and that can create channels that will exacerbate short circuiting in a lagoon. So with surface aeration and to some extent with subsurface aeration, you can change the orientation and placement of these aerators to help improve your overall treatment process for the lagoon. So just an example here of a couple of things that we run across out in the field. We've seen one lagoon. It was a small lagoon, had a couple of surface mixers centered in the lagoon, and they had short circuiting right around those aerators from the inlet to the outlet channel. Just moving those aerators slightly over into that flow path helped break that up, and they got better treatment capacity out of that lagoon cell. Same thing if you've got a regularly organized pattern here, you can see 3 rows of staggered aeration. So it's higher aeration at the front of that lagoon with a little bit less towards the end. They ended up creating a flow path right between a column of those aerators. Staggering those and offsetting them a little bit helped break that flow path up and make sure they were using the full volume of the lagoon and breaking up that short circuit. Something to look at if you're doing renovations or early design for a lagoon is how are you placing the piping? What kind of design are you using for that piping? Minimizing 90-degree bends and things like that can help reduce the frictional head in those piping setups. And this is beneficial for both sludge or wastewater piping, sludge piping, and your aeration blowers. The more you can reduce that head pressure in the system, the less horsepower you need overall to drive the aeration process and the pumping requirements. And so that saves energy long term. And really, for the upfront cost of looking at these designs, there's a very minimal impact on upfront capital cost. It's the same materials, you're just using slightly different fittings and junctions for these piping setups. Quick and easy control for aeration is using time clocks. We talked earlier about there's diurnal loading patterns, there's impacts from algae, things like that during the day. Time clocks give you a way to adjust your aeration profile to account for those different natural DO sources in your water. So during the day when algae's cranking out DO into the water, maybe you can dial back a little bit. In the evenings when you're getting a large loading coming into the plant, typically with people coming home from the office, they're starting to shower, clean, do dishes, things and stuff at home. You get that evening surge in loading. Then you might need to ramp the system up, and then overnight, as people have gone to sleep, you don't have that loading, you can dial back again. Timers can help do that kind of scheduling in your process. But you do need to do some research ahead of time to know what that loading profile in your lagoon looks like. If you have variable frequency drives in place already, are they actually helping you save energy? Are they in an automatic position where they're going to adjust based on conditions, or are they in manual? And have they just been set to full speed and not really doing anything to help you? So checking those things and making sure if you've got VFDs in place that they are actually helping you save energy. And if they're not, figuring out what the issue is and resolving it so that they can work properly for your process. One of the things we do recognize with lagoons is they are harder to automate. You've got a lot of surface area and a lot of areas to take samples at in a lagoon. It's hard to say from sampling at one specific point that the entire lagoon is performing appropriately. But in general, sampling is recommended at the effluent of each lagoon cell. If you can put a sensor in that area, you can automate that process. Those sensors can report to a central SCADA system. It can help you build out the DMR reports that you need to turn in. So you can save a little bit of labor from just a little bit of automation. You don't have to put sensors all over the lagoon or anything. You do still have to take your manual sampling at different locations through the lagoon to make sure that the entire process is working appropriately. But putting just a sensor or two to monitor those effluent channels at each lagoon cell gives you an overall performance. It can help you track if you're getting your appropriate aeration and processing. Couple of things that you might want to check. DO is the big one. Ammonia and suspended solids or other things you might track in those. And those can help reveal early if you've got a lagoon issue. So that automation process can also help tie into aeration devices and automate how they react to loading coming into the lagoon, where you don't have to do manual sampling and daily updates and checks and manually adjust those things. So now I'll turn it over to Dr. Moore. And let me give you control of your slides there. You should have access now. And you're muted.
There we go. Now can you hear me?
Yes, we can.
Yeah, thanks, Sean. It's a pleasure to be with you today. And we're going to talk about some no and low cost options for improving activated sludge. And I've had the opportunity over the last 13 years to visit about 100 activated sludge plants in the southeastern U.S. and do energy assessments. So I've been out there a lot and helped to share some of what I've learned over the last 13 years with you. But we're concerned about energy because if you're operating a wastewater treatment plant, we're concerned about our annual O&M costs. And usually energy costs are going to be about 20 to 40% of our total operating costs. Okay, there we go. All right, as far as an outline, we're going to talk about automatic DO control, facilitating denitrification and oxidation ditches, and then also trying to achieve denitrification in SBR processes. And you might say, well, Dr. Moore, why are you focusing on oxidation ditches and SBRs? Well, here's the reason. Of all the cities in the United States of America, 96% of them have a population less than 50,000 people. So what that means is 96% of the cities in the United States of America have a wastewater treatment plant that's probably designed for less than or equal to 10 MGD. And so that's why I want to focus on those. And a lot of those facilities are oxidation ditches, and quite a few of them are SBRs. And and again, I think there are something like 10,000 oxidation ditches at municipal treatment plants in the United States. So again, that's why I want to focus on these. It's mainly what we see out there. Just a little diagram of activated sludge here, because that's what we're talking about. We know what we're trying to do. Wastewater comes in, it's got organic load and nitrogen loading, and we're trying to run the process. I think arguably we can say there are three general goals that we want to achieve in activated sludge. Number one, we want to produce a good settling sludge. Number two, we want to produce excellent effluent quality. We want to consistently meet our NPDES permit requirements. And number three, we want to operate the plant efficiently. So we want to look at activated sludge and see what we can do with the aeration system, and one to make it more efficient. And one way we can do that is providing automatic DO control. And the goal again is to supply the amount of oxygen our biomass need, and to do it in a very efficient manner. We can easily waste energy by over aerating, and we don't want to do that. So aeration system is very important to activated sludge if we're trying to create an aerobic environment. And just to give you an idea, in a conventional activated sludge plant, usually about 50% of your overall energy use will be in the aeration system. In an extended aeration activated sludge process like oxidation ditch or SBR, usually about 60% of your energy use will be in the aeration system. So that's why we focus on the aeration system. Now, there are ways that we can save energy, and one way is using automatic DO control. And the reason we want to do that is because our oxygen demand in our activated sludge process, it's changing throughout the day. It changes on an hourly basis. Typically, at most small to medium municipal wastewater treatment plants, you'll have your peak oxygen demand from about 10 a.m. to 2 p.m. You'll have your minimum oxygen demand from about 2 a.m. to 6 a.m. And the peak hourly demand divided by the minimum hourly demand, that ratio is generally 2 to 1 to 5 to 1. So the oxygen demand is varying throughout the day. So we want to try to use automatic DO control if we can, so we're only supplying the oxygen that we need during any hour of the day. And so we need to keep that in mind. And another thing, again, we got to worry about is what's controlling our oxygen demand? Well, mainly it's how much carbonaceous BOD and nitrogenous BOD is coming in the influent. And if we're an activated sludge process and we operate at a sludge age or MCRT or SRT, whatever you want to call it, the age of the biomass, over about 10 days, then you're going to be doing an excellent job of nitrification. You should be converting at least 90% of the ammonia to nitrite and nitrate, mostly to nitrate. And so it's going to be very efficient in nitrification. And if you're doing that, about 70% of your energy use or aeration requirements will be for carbonaceous BOD removal, and about 30% will be for nitrogenous BOD removal, or the conversion of ammonia to nitrate. The nice thing about DO control, if we haven't been using it and we implement a DO control system, an automatic DO control system, we should be able to achieve 10% to 30% reduction in our overall energy costs. So that's important to us when we operate a treatment plant. And again, it depends on the type of plant you have and what you're doing right now. You may not be doing any DO control right now, and if you aren't, then there's a lot of opportunity for you to save energy. And in the payback period, if you install an automatic DO control system, put in DO probes in your reactors, and connect it, do the connections that you need to your PLC, and provide automatic control, you're going to spend some money, but typically it will pay for itself in 2 or 3 years in terms of energy savings. So what do? We put DO probes out in the aeration tank. If we're a small treatment plant, maybe a 1 MGD plant, we might have 1 or 2 oxidation ditches. We might put 1 DO probe in each oxidation ditch, and that information will be recorded instantaneously and sent to the PLC. And then the PLC then can control our aerators. And if it's an oxidation ditch, typically we're using either horizontal rotor aerators, or we may be using slow speed vertical aerators to provide oxygenation and mixing. But try to control the speed of those aerators, or possibly turn aerators on and off as needed to meet our oxygen requirements. If we're a conventional plant and we have diffused aeration, then we can use that information to control the speed of our blowers or how many blowers are operating. So again, we got a feedback control loop. We're going to measure DO at the appropriate location and send that information to the PLC, and it'll allow us to control the amount of aeration that is operating at any given time. And by making it automatic, we can, again, supply just the amount of oxygen that we need. Now, again, if it's a small plant, 1 or 2 MGD, we want to keep it simple. Maybe 1 DO probe per basin, and we may want to use on-off control of the aerators, or we may, if we have VFDs on the aerators, we can control the speed of the aerator. So we can do that with a simple system. If it's a large treatment plant greater than 10 MGD, then more than likely we'll have a complicated or complex DO control system that may involve proprietary algorithms. But again, I mainly focus on the smaller plants. All right, well, so that was a general assessment of how we can use DO control to save energy. Now what we want to do is look at oxidation ditches first, and see how we can incorporate an anoxic period to achieve denitrification, how that'll help us save energy. Now, what we need to understand is, let's say you have an oxidation ditch right now that is operating fully aerobically. In other words, you may be providing 1.5 to 2 milligrams per liter DO 24 hours a day, 1,440 minutes a day. That's okay. And you're going to produce a good quality effluent, low CBOD, low ammonia nitrogen, but you'll be sending a lot of nitrate nitrogen out in the effluent. But what I need you to understand is oxidation ditches, the way they're designed, they're about 2 to 4 times larger than they need to be to get efficient CBOD and NBOD removal. So because of that fact, what we want to do is take advantage of that excess volume to achieve denitrification and help make the process more efficient. Being a former professor, I love to talk about biokinetics and facultative heterotrophs and autotrophs and all this stuff. But again, what we got to realize is that the BOD load that comes into the treatment plant, it gets channeled in 2 directions. Some of that BOD load is going to be channeled into growth reactions or synthesis reactions. We're going to grow biomass, and the other part of that BOD load is going to be channeled into energy or oxidation reactions. And we as a design engineer, and you as the operator, you're going to control how that incoming organic load is channeled. If you operate at about a 3 or 4 day sludge age, most of that BOD is going into the growth reaction. You're going to produce a lot of waste biomass, but your oxygen demand will be lower. If you're an oxidation ditch operating at a 30-day sludge age, you're not going to generate a lot of biomass, waste biomass, and most of the BOD load is going to be channeled into the energy reaction. You're going to need more oxygen. And so, again, we have different bacteria, but what we have to realize is in our mixed liquor, most of our bacteria are facultative heterotrophs. That means heterotrophs means they use organic carbon as their carbon source. There are BOD or organic matter reducing bugs, okay? So that's the vast majority of our bacteria. And most of those heterotrophic bacteria are facultative. What that means is if you give them oxygen above 0.3 milligrams per liter, they're going to operate in the aerobic mode. But if you allow the DO to get below 0.3 milligrams per liter, between 0.0 and 0.3 milligrams per liter, now they can begin to use nitrate or nitrite as their electron acceptor. And won't get into a lot about that, but the way the bacteria generate energy is through the electron transport system, and the electron acceptor is very important. But if they're operating aerobically, oxygen is the electron acceptor. If they're operating anoxically, which is their second preferred mode of operation, then they're going to use nitrate primarily as their electron acceptor. And if you take away the oxygen, take away the nitrates, then you're going to force them into the anaerobic mode. So that's how we create an anaerobic reactor. Take away the oxygen, take away the nitrates. So, we as a design engineer and you as the operator, we're going to manipulate the bacteria to achieve the kind of metabolism we want. So we need to keep that in mind. So when we denitrify again, as opposed to nitrification, when we nitrify, we depend upon the nitrifying bacteria, and they are autotrophic. That means they use inorganic carbon, primarily carbon dioxide, as their carbon source. And they're obligate aerobes. They're like us. They're obligate aerobes. They have to have oxygen as their electron acceptor. And so they're obligate aerobes. So when we denitrify, we don't use those autotrophs. We're going to go back to our BOD, our carbonaceous BOD removing bugs, our facultative heterotrophs. And again, we're going to allow the oxygen preferably go down to 0.0 milligram per liter and force those bacteria, take away the oxygen. They're going to look next for nitrate. And if nitrate's available again, they're going to operate in the anoxic mode. And so we're going to manipulate the process to try to achieve energy efficiency and denitrification. Now, what controls the denitrification rate? Well, these are the four factors that primarily control the rate of denitrification when the reactor is anoxic, okay? And you can see I've highlighted substrate degradability and dissolved oxygen because those are by far the two most important. The rate of denitrification, or the rate that the nitrate is converted to nitrogen gas under anoxic conditions, depends on the amount of readily degradable organic substrate in the wastewater. The higher the readily degradable organic substrate concentration, the higher will be the denitrification rate. And we look at dissolved oxygen, the lower the dissolved oxygen level, the better. 0.0 milligram per liter of oxygen is the best level to achieve denitrification. And again, if you get above 0.3, they're going to operate aerobically, and so you're not going to denitrify. So again, we can denitrify between 0.0 and 0.3 milligram per liter of DO. Okay, what were some of the benefits of denitrification? Well, we're going to reduce the total nitrogen loading on the receiving stream. That's good. That's really good. We're going to generate alkalinity. That's going to help us keep us from having, we know when we nitrify, we consume about 7.1 pounds of alkalinity for every pound of ammonia nitrogen that gets converted to nitrate. But when we denitrify, we're going to get about 3.5 pounds of alkalinity back for every pound of nitrate that gets converted to nitrogen gas. For every pound of nitrate that gets converted to nitrogen gas, we're going to save about 3 pounds of oxygen. So if we create anoxic conditions within our ditch or SBR process, we're going to achieve probably about 10 to 15% oxygen savings because of that oxygen savings due to denitrification. This shows you the impact of DO. So when we, in an anoxic basin, we want the DO preferably to be 0.0 milligrams per liter because we're going to be operating at 100% of our relative denitrification rate. And you say, why relative? Well, again, the denitrification rate also depends on how much readily degradable organic matter you have, okay? But so you can see why we want to operate at 0.0 DO. If the DO is 0.3, we're only going to get about 10% of our maximum denitrification rate at that DO, okay? So DO is very important to denitrification. So what can we do to the ditch? We want to modify the ditch, the way we're operating it, so we create an anoxic zone and enhance denitrification to achieve the benefits that we talked about. And we can do that with on-off operation of the aerators, or we might try to turn some of our aerators off and create an anoxic zone in parts of the ditch. I'll show you that in just a moment. And then we can also modify our sequencing batch reactor to include anoxic zones as well. So let's say here's our oxidation ditch, and we got, as you can see, we got 4 horizontal rotor aerators that are supplying oxygen to the ditch. Our influence coming in here, and our return activated sludge is coming in here. So what we may want to do is turn this aerator off and this aerator off, and that's just downstream of, again, of where the influent is coming in. And you say, well, if we turn both those aerators off, we may not get enough oxygen to our biomass. Well, that's true. But what you got to realize is that many of the municipal wastewater treatment plants in the United States are operating at about 25 to 50% of their organic design capacity. Okay. So that gives us a lot of opportunity with our aeration system to be flexible. Now, if you're a plant in this particular ditch, if you're loaded to like 85% or 90% of your organic design capacity, you probably don't want to turn off 2 of these rotors because you may not get enough oxygen to satisfy your total oxygen demand. Okay, another approach is if we've got a ditch that's fully aerobic, well, this goes back. This shows you what we're talking about here. Again, what we'll do is turn off these 2 aerators shown here, and we may or may not include a mixer. We don't have to include mixing in that anoxic zone. But again, by turning those 2 rotors off here and here, and hopefully we can create anoxic conditions in this portion of the ditch. And the size of that anoxic zone is going to fluctuate depending upon the way we're operating the plant and depending upon our organic and TKN loading coming into the treatment plant. Okay, another thing we can do, and I'm really high on this approach, and that's turning our aerators off and on during the day. What I usually recommend is that you turn your rotors off maybe 3 to 6 hours a day, and by doing that, while the aerators are off, the DO is going to go down to 0 in about 15 or 20 minutes, and we'll have 3, 4, or 5 hours of anoxic metabolism taking place, and we can achieve excellent denitrification even if we're not providing mixing. Just even the biomass settle, which it will, we can still achieve real good denitrification in a ditch by turning our rotors off. And you might say, well, Dr. Moore, if we do that, how do we know how many hours we should turn it off? Well, you can do it by trial and error. You can start with 3 hours. If that works good, go to 4, then maybe to 5, and see how your ditch responds. And then another way is to use an ORP meter to kind of see what's going on. And this diagram shows you what we're talking about. When we got the aerators on in this zone right here, the DO may be up around 2 milligrams per liter. At this point, we turn the aerators off. And again, let's say we got 2 milligrams per liter DO. Well, in a typical ditch, the biomass is using the oxygen uptake rate is usually about 0.1 milligram per liter per minute. It might be 0.2 milligram per liter per minute, but let's say 0.1. Well, if the DO is 2 and they're using oxygen at 0.1 milligram per liter per minute, it's going to take 20 minutes to go from 2 DO to 0 DO. So it's still aerobic here. So once we get to this point, now we got 0 DO. And so in this zone right here, now we have an anoxic period. You see DO is up here, then it goes down to 0. And in this zone, the DO is 0. So while we're in the anoxic zone, DO doesn't really tell us a lot. But we can use the ORP, and the ORP will give us a much better indicator of what's going on in the anoxic period, during the anoxic period. So ORP during the aerobic phase, when DO is 2, it may be up around 200 to 300 millivolts. And then when we go down to right here and DO gets depleted, we may be at plus 50 millivolts, just ballpark. But by the time we use up all of the nitrates, then the ORP at this point might be minus 150 millivolts. Again, I'm just throwing out ballpark figures here. But again, this is the point that we want to turn the aerators back on, because we depleted all of our nitrates, and you can see the rate that the ORP is changing, going to change dramatically, because now we kicked it into an anaerobic mode. So again, the ORP can tell you a lot about what's going on in the during the anoxic zone. So what are the factors we need to look at in on-off operation? The hydraulic detention time, the influent flow rate, the TKN and BOD loadings in the raw wastewater, how many on-off cycles we use per day, and what our ditch MLSS concentration is. But let me just say this. There are some conditions if you've got an oxidation ditch where you probably don't want to use on-off operation. I'm going to give you 3 conditions. Number 1, if your monthly average effluent NPDS limit on ammonia nitrogen is 1 milligram per liter or less, you probably don't want to do this, because if you use on-off operation, when the aerators are off during the anoxic phase, that ammonia concentration is going to inch up to about 1, maybe even 1.5 milligrams per liter. If your hydraulic detention time of your ditch is less than 18 hours, you probably don't want to use on-off operation. And then the other factor is if your influent TKN concentration is above 40 milligrams per liter, you probably don't want to use on-off operation. What's the expected effluent quality if we use on-off operation? Well, roughly, again, these are ballpark. We expect our BOD to be about 5 to 15, suspended solids 10 to 20. Ammonia usually with on-off, I usually expect to get 0.5 to 1 milligram per liter. Nitrates, nitrite, NOx combined, nitrate combined 5 to 10, and then total nitrogen about 7 to 14. And what I need you to realize is the difference between this and this, we have to add to our nitrite and nitrate, the ammonia nitrogen and the organic nitrogen to get total nitrogen. All right. In a typical municipal wastewater treatment plant effluent, we're going to have about 1 milligram per liter of dissolved non-biodegradable nitrogen in the effluent. Okay. And typically, if we got about 10 suspended solids going out in the effluent, we're going to have about 1 milligram per liter of particulate organic nitrogen in the effluent. So typically, for most activated sludge plants, unless they've got a certain type of industry that sends them a lot of organic nitrogen, normally you'll have about 2 milligrams per liter of organic nitrogen in your effluent. So if we got 5 milligrams per liter of NOx, which is nitrite and nitrate, we got a 0.5 milligram per liter of ammonia, that gets us to 5.5, and then we got 2 milligrams per liter of organic nitrogen. That gets us up to about 7.5 milligrams per liter of organic nitrogen. Let's talk a little bit about SBR very quickly, and then we'll wrap it up. In an SBR, again, sequencing batch reactor, again, it's extended aeration activated sludge. It's just in the batch mode. And so if we're a typical SBR and we're fully aerobic, we'll do an aerobic fill, aerobic react, settle, and decant. But what we want to do is to save energy and try to denitrify and reduce the amount of nitrogen going to the receiving stream. We might want to use half of our fill period, let that be anoxic, and the other half of the fill period be an aerobic fill. And that'll be half of our total. Let's say if we got 2 batch reactors, then one reactor, it'll receive the wastewater. Let's say it's a 6-hour cycle. Then one reactor will get wastewater for 3 hours, and the other reactor will be in a 3-hour period that includes react, settle, and decant. So the cycle might be 3 hours fill, 1.5 hours react, 3/4 of an hour settle, and 3/4 of an hour decant. So again, we can provide anoxic and aerobic conditions during the fill period when the wastewater is coming into the SBR reactor, and then we stop the fill and go into the react phase. We can alternate between anoxic and aerobic conditions to achieve denitrification. And if we do that in SBR, and this is approximately the effluent quality that we can get, and you might see it's a little bit better than what we had for an oxidation ditch, and that's because in SBR, when we turn our aeration off, we got almost a perfect quiescent settling tank. It's not a continuous flow settling basin. It's a perfect quiescent tank, and the solids are going to settle very well, and usually we produce a better effluent with an SBR slightly than we can with an oxidation ditch. So that pretty well wraps me up. Thanks a lot for listening.
Well, thank you, Dr. Moore. We'll turn it over to Nick.
Let's see here. Am I able to advance it and all that?
You should be able to. Yep. I see your mouse moving around.
I see. Okay, just testing it out. All right. All right. Hi, everybody. Good morning. My name's Nick. I work at the Kishwaukee Water Reclamation District here in DeKalb, Illinois. I'm the environmental analyst on staff. And so my perspective on, these no and low cost energy projects that we've engaged in to get a lot of, power consumption savings is from the perspective of, I help our energy team, which is, our chief operator, our chief maintenance guy, operations manager, our technical services director, and myself. I'm involved in the kind of the organization and planning of the projects, following up with implementation, and analyzing the energy savings. So I'm not an operator, I'm not an engineer. I will do my best to go through this in a comprehensive manner, but just be aware my technical knowledge of process is not necessarily where some of you might be. So a little background on the district. We were originally organized in 1928 as the DeKalb Sanitary District. That reflects the fact that at that time, we were treating wastewater really only from the city of DeKalb, which is where our facility resides. As of about 4 years ago, we transitioned and reorganized into the Kishwaukee Water Reclamation District. We're slowly becoming a regional entity, so we're expanding beyond the bounds of DeKalb. We currently serve about 45,000 users, a lot in the city of DeKalb still, but we also just took on the collection system and wastewater from the village of Malta, which is a municipality directly to our west. We also treat the wastewater from Northern Illinois University, Kishwaukee College, which is a nearby community college, and some residents and industries in unincorporated DeKalb County nearby. Our facility certainly falls into that kind of small to medium size range that Dr. Moore was referencing. We're rated at 8.63 MGD. Our average daily flow is around 5. And with this expansion that we've recently done to these other areas, we are now sitting at about 185 miles of public sewer in our collection system with 11 pumping stations that involve force mains. So a little background on kind of how we got involved in, these energy improvements and projects. District administration has always been very forward thinking, but really this kind of got kickstarted when we had a major treatment plant overhaul and expansion capital improvement project that closed up, I believe, 2019, 2020 in that range. And this project gave us, a lot more of the sophisticated activated sludge through biological process control, gave us a lot more controls. Everything pretty much now is controlled by our SCADA system, a lot more sophisticated sensing equipment, and it kind of gave us the ability to better experiment with the process on pretty much a minute-to-minute basis. And also, this project allowed us to start generating our own power on site. We have 2 combined heat and power generators that utilize our biogas from our anaerobic digesters, which was something that, got us very excited about, other potential energy consumption reductions to help us meet, our own consumption. We've had a lot of openness to innovation and change as far as how we do things, how can we do it better from our administration. So that's been kind of a through line through this whole phase 1B and beyond. And also in February of 2022, we began engaging in a program through ComEd called the Strategic Energy Management Program, or SEM. It's a voluntary, attendance group where it's a cohort of other treatment plants that essentially you get access to, these experts at ComEd who have worked with treatment plants to devise strategies to reduce consumption and change processes, as well as, the ability to use this platform called Energy Sensei, which essentially just lets you kind of organize your projects and, have things all in one place to kind of see what your potential savings are. I just wanted to touch again on kind of some of the things that excited us a lot and got us going on all these energy projects. The main thing that really got us excited was this on-site energy production. We have 2 375 kilowatt CHP units that utilize the biogas from our 4 anaerobic digesters. You can see in this picture here, we've got all the gas treatment equipment. Our generators are inside this building. And, you know, if we have enough biogas and our generators are both operating at full capacity, on any given day with those conditions, we can produce about 115% of our electrical demand. So we're able to actually exceed our consumption with our production. Again, a little bit more about SEM. You know, we really look at it as kind of a launch pad to start engaging in a lot of these changes and projects. You know, I mentioned we get access to these ComEd experts that have done a lot of work at other treatment plants. This is just some kind of snapshots I took of our dashboard on the Energy Sensei website. So, you know, one thing you get access to is kind of like a interactive timeline that shows savings. So this green line is our actual energy usage. Blue line is our projected energy usage for the same time frame, and through that it generates a you know, a potential cumulative energy savings through line. We also have the ability to use and look at dashboards that kind of show us for any given time range, kind of what our potential savings would be, either from projects we've implemented specifically or other things. This dark blue is our energy production. So kind of gives us the ability to see it all in one place. And then kind of an overview of, you know, the types of projects and how we've begun implementing them. A big part of this whole thing is, you know, shifting our focus towards actively driving the plant processes, right? So, you know, kind of having our hands in the pot, so to speak, across the whole process, actively looking at and driving the way the plant functions on a day-to-day and a minute-to-minute basis. And, you know, really kind of questioning how things are done, how they have been done. You know, just because something's been done a certain way for a long time doesn't mean it's the right or best way to do it. As far as actually implementing these projects, which I will go over a lot of our projects coming up, but kind of our philosophy is something that is called tweak and peak. So the idea is you make very small changes to a specific part of the treatment process, and then you see kind of, you take a step back and you see what the effect is. What is the effect on, you know, our effluents? How is it affecting our equipment? How is it affecting our ability to, you know, biologically, you know, denitrify and remove certain nutrients? And the idea is you don't want to do too much too fast, because, you know, it's hard to predict with how complicated the process is, just what effect a large change will have, you know, if you do too much too quickly. So, you know, again, tweak and peak, little small changes. You might not even notice energy savings until a couple months down the road, when things kind of compound, and as you make small changes incrementally, they make a big difference over time. And, you know, being uncomfortable is okay within reason, right? So, you know, like I said, you can't always predict what's going to be the effect of a change that you make to, you know, run times or set points, something like that. And as long as you're being careful and you're being methodical and doing things, you know, in small steps, it's okay to be uncomfortable, because it's all new territory, you know. As far as kind of the types of projects we've engaged in, generally they fall into, you know, one of three categories. So, you know, there's set points, which obviously we're doing mostly through our SCADA system and all of our automation. There's adjusting run times and timers for different pieces of equipment, whether they're, you know, motors or pumps, and then kind of adjusting our standard operating procedures as far as, you know, on the day-to-day basis for our operators and our maintenance staff, you know, the way they do things on a more day-to-day basis, you know, kind of changing the perspective of, you know, how do we do things more efficiently and more sustainably. This here is just another screenshot of that SEM Sensei website platform. You know, so it's useful because you can kind of have all your projects in one place. It'll show you at what point in the process you are, you know, when certain projects were completed. But again, you know, you don't have to have this platform in order to do this. You can do this on Excel. You know, it's just this is a useful screenshot, I thought, for kind of showing what it can look like to organize a lot of that. Okay, so as far as what we've actually done, I kind of want to highlight a couple of our big hitter items. Each one falls under one of those project types. So this would be essentially a set point adjustment. So I know there was interest in talking about what happens when you raise, your wet well. So for us, we've only adjusted our raw wet well. And before we did any of these projects, it was at 5.5 feet. And, over the course of about the 2 years, 1.5 years that we've been involved in doing all these programs very actively, we've slowly raised that, about half foot here, half foot there, a couple months apart. And so we've adjusted it by about 2.5 feet. It's now sitting at 8 feet, which, I've got pictures here of the same panel actually showing before the changes and after. So, it dropped our amperage from about 156.5 to 150.5 roughly. So about a 6 amp reduction, on a, power supply 480 volt 3-phase. And because of the fluctuations involved, in the VFDs, it's hard for this particular case to get an exact concrete number as far as power reduction. But in speaking, with our operations staff and with some of the folks at ComEd, the industry standard for a change in our wet well level like this equates generally to about a 10% overall power reduction, which calculated out is about 65,500 kilowatt hours per year that we're saving on consumption, which equates to about $5,200 a year, which is certainly not nothing. Next, we have our second project type generally is runtimes. So this was a really big ticket item for us. We have 4 anaerobic digesters. 2 of those are secondary digesters that each have a 50 horsepower mixer motor. You can see our digesters in this nice picture here. Previously, before we did anything, we were running them in a cycle of 75 minutes of active mixing and 15 minutes of idle or off time. And we, after doing some investigation and making incremental changes, we discovered we were running it way more than we needed to. And at the point we're at now, which is getting close to the bottom threshold of where we feel comfortable making changes, we're now running them on a cycle of 45 minutes of active mix time and 30 minutes off, which calculated out as 8.5 hours of less mixing per day, which is pretty huge. I mean, and as you can see, that's calculated out, if things are run consistently in this new way, it's about 232,000 less kilowatt hours of energy consumption a year, which is about $18,500 in savings. So this was definitely a very, heavy hitting project for us. And we were really happy to see that we could run it so much less. The final kind of spotlight project I have is involving our UV system. So, we run our UV system as disinfection rather than chlorine, and we run it from May through October, because that's when the disinfection is most necessary. By working with our maintenance staff and implementing some set point adjustments, which I personally don't know the exact particulars of, and also by creating a frequent cleaning schedule, since we started them up this past May, we were able to calculate that we're getting about 141,500 kilowatt hours less consumption on an annual basis. I mean, for that 6-month period, which equates to 800 kilowatt hours less per day that we're consuming for our disinfection to still get disinfection that's, well within permit. And that equates to about $11,300 per year that we're saving. So, I mean, across just these 3 projects, that's, almost $30,000 that we're saving a year, which is pretty, actually over 30,000. It's pretty spectacular. I kind of want to just go over a couple other of the, types of projects we've gotten involved in that kind of just cover all our bases. So one thing we've, eventually kind of had to shift gears on as far as standard operating procedure is just turning off air handling units in places that are either unoccupied or are not occupied very often. It's a waste of power, it's a waste of gas. There's not really a point in keeping that stuff running if there aren't people that need, the comfort brought by, heating and stuff like that. Reducing our waste activated tank blower pressure and airflow. We reduced that from 50% of its maximum down to 30% of that flow. And previously we were running those continuously. So we were running that blower for our 24/7. And we were able to find that we reduced that down to only 10 hours a day to still get good waste activated sludge. Another one in our biosolids processing system that we have, we use non-potable water booster pumps to help get water through the piping up to our dewatering and our centrifuges. And, we were over pressure for what we really needed. So we dropped that from 90 to 75 PSI. Involving pump speed, we use, boiler recirculation pumps for our digesters. So we reduced speed for the two primary digesters from 275 GPM to 175 GPM. And I don't have it on here, but for our secondaries, we brought that down to only 150, and we're still getting good digestion. Turning off our air to our WAS storage tank during the off hours, we found that we can reduce that airflow and still, like I said, still get good waste activated sludge. And then for our TWAs, again, a pump speed reduction going down from 45 GPM to 30 GPM, has not presented any problems for us. And so, like I said, these are some of the spectrum of the different changes that you can make at a treatment plant. And, as you make them little by little, you can see you can still meet permit, you can still have a good functioning plant, but also save a lot of energy and a lot of runtime. So beyond just the actual consumption reductions and the energy savings financially, there are certainly non-energy related impacts that doing all these projects and kind of getting a more sustainability focused mindset have had. So first of all, theoretically, some of this is too recent to really be able to quantifiably verify this, but theoretically, reducing runtimes and load on a lot of our equipment should extend the equipment lifespan, Certain equipment, you have to do maintenance at a certain amount of hours, or, some equipment only has a certain lifespan of run hours. So by reducing the amount of time and load that's being put on the equipment, it should extend a lot of the lifespan for this equipment. As far as labor hours and kind of overall, staff morale, one thing that when you start doing these kinds of projects that you need to be aware of and to have a plan for is, the idea of backsliding. So, let's say, kind of like Sean had mentioned, you have equipment that's automated that should be in automatic mode because you have timing schedules or you have certain, runtime scenarios. And sometimes people just put it in hand. And backsliding, is the risk of when you have certain projects implemented and you have a new method of doing things, people kind of fall back doing things the way that they have previously done it. So you need to be aware of that risk because it certainly exists, and getting everybody on board with the new way of doing things. Another thing to kind of keep in mind is, what a concern would be, how is this going to change our labor hours? How much time do people have to spend on, the equipment and running things in these new methodologies? And it really hasn't changed anything in the long term for us, at least not quantifiably. Nobody's said anything either as far as morale goes. At first, perhaps, there was an increase in labor just getting used to the new process, but that's a very short time frame. Once people are aware of the changes and adjust to them, there's not really been any concerns with increased labor hours. And then as far as kind of involvement and enthusiasm, just on a district-wide level, really the entire staff, our operators, our lab, our maintenance staff, everyone is much more aware and involved in how the plant functions now because, we're constantly trying to think of new ways to do things, and it gets people excited about, how much further can we push it? And, just for some people not maybe having been as aware of how things worked until they started seeing how the changes affected the treatment process. And like I said, just kind of always looking for new improvements and seeing where we can go from here. Again, just some final thoughts. When you're doing a lot of these energy projects, right, you got to balance the innovation with your plant health. So openness to change, right, at all the levels. Everybody's got to be pulling in the same direction, making those small incremental changes, right? Make a tweak, take a step back, see what happens before you make further changes. Make sure that things aren't going, out of balance. And then, bottom line is that we still have to treat the wastewater. We still have to meet permit. The equipment still needs to run how it's supposed to. And so, it's balancing these energy savings and trying to reduce consumption with still making sure that the plant is running how it should. And then, again, a last final thought is just keeping up, being persistent with the projects, always kind of looking for new ways to save and thinking long-term about it. So again, you need to assess that risk of backsliding, make sure if you need to, you create signage, hey, keep this in auto mode, only put in hand in, big wet weather events or something like that, just so people are aware that it's important to make sure that these changes stay the way that we're now implementing them. And like I said, just getting everyone aware of the new processes, trying to get them excited and actively involved in the treatment process, and just everybody pulling in the same direction. So that's what I have for you folks for now. Thank you very much.
All right, thank you, Nick. So thank you to both our guest speakers for talking today. I'll open it up to questions from the audience now. We're right at noon, so if you have to go, I understand. But we have one question here. For small plants with oxidation ditches, what's the recommended setup for aerobic anoxic zones from heavy ammonia recycle loads? You're muted, Dr. Moore.
Yeah, that's a problem we have to deal with sometimes. I assume that's a recycle stream coming back from sludge processing, and it may have 150, 200, 250 milligram per liter of ammonia nitrogen in it. So a lot of it's going to depend on what your effluent ammonia limit is. If you got to meet a monthly average effluent ammonia nitrogen limit of 1 milligram per liter, and you got that much ammonia coming back in a recycle stream, you may not want to use on-off operation, because again, it's going to cause your ammonia nitrogen to creep up in the final effluent.
One other question that I've seen was one of the concerns we've heard from operators is turning off equipment and dealing with settling of sludge, particularly with subsurface aeration. Just some concern of clogging of those pores and not being able to resuspend those solids.
Right. Yeah. If you got a diffused air system, it's a different game. Again, I'm dealing with oxidation ditches primarily, and most of them either have horizontal rotor aerators or vertical slow speed aerators. Some ditches do have diffused aeration, and that's an issue. So if you got a diffused aeration system and you got fine bubble diffusers, that's certainly something you got to be worried about, especially if they're the ceramic disc type diffusers. They will plug, and that's a problem. If you got the flexible membrane diffusers that give a little bit, you may be able to turn the blowers on and off. But with diffused air, it's a different ball game.
I think that's all that I've seen come in. Cassie, have you seen anything else come through the chat?
I have not, no.
All right. Well, thank you both, our presenters today, for presenting and helping us out with this webinar. Hope it's been informative for everybody. Have a wonderful afternoon.
You all as well. Thank you for
Thanks a lot.
giving me the opportunity.
Appreciate it. Y'all have a great day.
Yep. Take care, everybody.